So we left off chapter 5 review with classifying chemical reactions as combination, decomposition, single replacement, or double replacement. And as I said, this is one way of looking at, chemical reactions, where you look at, how many product or reactant do you have, and this can give you a clue if you have a combination or decomposition reaction. For single replacement and double replacement, the difference is that the single replacement will have an element plus a compound, and you make a new compound and a new element. And for the double replacement, it's two compounds that exchange partners, and you make two new compounds. And then there are other ways of classifying reactions. And for example, in your lab 4, you will see examples of precipitation reaction. And as I said, you've seen a lot of these in lab 2 already, where you saw white or other colors, but white precipitate or blue precipitate when you add copper, or dark green when it's iron, etc. So those powder that form within solutions when you mix two clear solutions, it gives a powder, and that's a solid. And so a precipitation reaction is recognized by the fact that you mix two aqueous solutions and they will give a solid. So one of the product will have S in its parentheses there to show the physical state is a solid for that one, for that compound. And precipitation reactions are double replacement, where there is an exchange of partner between the compound. You can see here A now is combining with Y to form a new compound, and then X is combining with B to form the new compound. Before I talk about combustion, let me continue with acid-base reaction. And I talked about it last time and told you there are also double replacement reactions, but there's many other type of acid-base reaction. This is true for the acid-base neutralization reaction. And the acid-base neutralization reaction is the simplest acid-base kind of reactions, where you have an acid plus a base, and you will get water and a salt. And that's why it's called the neutralization, because you go from a acidic compound and a basic compound to water which is neutral. So that's why it's called like that. And so why do you form water? It's because the acid contains H plus ions in solution, and the base contains OH minus, the hydroxide polyatomic ion. And together, when you put H plus plus OH minus, they form water. And then here we can see, if we write it with more details, and you will see that form in your lab 4. When you have the acid, and if the acid is symbolized as HX, because acids typically will have the hydrogen first in their formula. That's how we recognize acids. And then the base, the strong bases, there are many kinds of bases, but the most known and strong bases will have the hydroxide ion in their formula, and they will be combining with a metal, typically alkali metal or alkaline earth metal. The M symbolizes the metal. And so you see that the H plus here from the acid will combine with the OH minus from the base, again, to do water. So that's why you have water as the one of the product. And then the cation from the base here, M plus, because it's one OH, so M plus, it's a cation. It will combine with the anion from the acid, because the acid here has is made of the ion H plus and X minus. So that X minus here will combine with the M plus to form the salt, and the salt will have this generic formula MX. And the salt can be aqueous or solid. Sometimes it's going to be also a precipitation reaction at the same time than it's a acid-base reaction. But again, here it's a double replacement reaction where you see that, you know, H plus will go with OH minus, and then the M plus will go with the X minus, and you form new compounds. So yeah, I added this to the acid-base kind. And then we've seen combustion reactions. These are very important. I want you to recognize a combustion reaction for sure, because this is very specific. Those O and C's and H are not, you know, generic. They are carbon, hydrogen, and oxygen. So you can really tell what you get. So combustion reactions are a sub class of oxidation-reduction reaction, but they're very important on their own. So typically, when you have a compound made of carbon and hydrogen, and sometimes they also have oxygen, those organic molecules or covalent molecules, because it's all non-metals. They will burn with oxygen from the air. When you burn with oxygen from the air, you need to add O2 as a gas in your reactant, right? The oxygen we breathe, it's a molecule, a diatomic molecule made of 2 atoms of oxygen, and that's as a gas in the air. So that's why you don't see it, but it reacts with what you have, you know, like here, it's a liquid or a gas, typically the compound made of carbon and hydrogen. Or it could be a solid like wood, wax, all kinds of things that you can burn. So typically you need a spark to start this kind of combustion reaction, and then you will produce carbon dioxide and water. So the formula for carbon dioxide is CO2. It's a gas at room temperature. And water, it's H2O, and it's a gas because you're burning, so it's in the phase of vapor phase. So combustion reactions are a subtype of oxidation-reduction reaction. So we will look at oxidation-reduction reaction. And you know, here I'm doing some kind of lecture, and that's my review has not been made for that. But oxidation-reduction reactions are reactions where you have an oxidation occurring at the same time that you have a reduction occurring. To remember what is what, we have this an acronym oil rig. Oil for, let me write it here. So oxidation is loss of electrons. It's implied that it's of electrons. And R is reduction, is gain of electron. So we have this acronym to remember that oxidation is loss of electrons and reduction is gain of electrons. And when you have an oxidation-reduction reaction, there is a transfer of electrons from one element to another element. So one element is losing electrons and another element will gain those electrons. So that's why they go together, oxidation and reduction. You cannot have an oxidation without a reduction happening at the same time, because the electrons, they have to go somewhere. So oxidation reduction reactions are about transfer of electrons from one element to another. And so we have examples of oxidation reduction reactions here, and I'm asking you to determine which reactant is oxidized and which reactant is reduced. So when you have that kind of question, it's always about the reactant, right? You will see what they become. So don't list, for example, like in a quiz or a homework, don't list a product as being oxidized or reduced, right? The question is always asking for which reactant is oxidized and which reactant is reduced. So let's look at the first equation here. We have aluminum as a solid plus 2H plus aqueous yields Al3 plus, so the aluminum ion. So now dissolved in a aqueous solution, because when it's in that as an ion, it's soluble in water. And then H2 gas, so you're forming also the hydrogen gas. Hydrogen, just like oxygen, you see below here, hydrogen is one of those diatomic molecules that are elements, because it's made of just one type of atom. And that when you find hydrogen in nature, you find it as two atoms of hydrogen bonded together, and it's in the gas state. I don't know if you remember, but there are 7 like that, right? Let me see. Hold on. If I remind you here briefly, the 7 diatomic molecules that are elements are hydrogen here on the left side, nitrogen N2, oxygen O2, fluorine F2, chlorine Cl2, bromine Br2, and iodine. And there are gases. Hydrogen is a gas, nitrogen, oxygen, fluorine, chlorine are gases. Bromine is a liquid, and iodine is a solid. So they are not all gases. So please tell me in the chat which of the two reactants do you think is oxidized? Let's start with the oxidized one. So oxidation is loss of electrons. So you want to find the reactant that has lost electrons going from the reactant side to the product side. So remember, when you're losing electrons, you're losing negative charges, and an element keeps its protons. You don't touch the protons, they stay the same number. And so if you're losing electrons, there are negative charges that go away, and then you're left with protons that are not cancelled out anymore, and that will show up as positive charges. Yes, right? Aluminum. So I should have said that also earlier. So aluminum as a metal, and that's true for all metals. When you see a metal symbol with a S as is a physical state, it means it's the metal in its elemental state, like you see it in the periodic table. And metals are all solids except for mercury. So that's why they are all S for solid. And in their elemental state, we say that their oxidation state is 0. It's neutral, right? So here, aluminum is neutral on the left side, and it becomes Al3 plus, right? It becomes an ion with 3 positive charges on the right side. So for this to occur, aluminum has lost 3 electrons. Those 3 electrons are gone, and now we have 3 protons of aluminum that are not cancelled out anymore, and that shows up as a 3 plus, right? So that's why, yes, aluminum is oxidized. Oxidized into Al3 plus. By losing 3 electrons. So tell me now which one is reduced, and once you've found one, the other one is automatically reduced. Yeah, so I know it's chat, but it is important here when you say H, that you say H plus, because H in the reactant side is an H plus ion, right? Yes. So please don't forget, it's important here to specify H plus. H plus is reduced H plus is reduced into H2, right? So it doesn't matter the fact that there is two hydrogen atoms, in H2 and only one atom of hydrogen in H plus. What matters is that H plus started with one positive charge, and to become H2, a neutral molecule. So for H2, O2, N2, Cl2, F2, those molecules I told you about, they are neutral when they are in that state of a diatomic molecule, as you find them in nature. So here H2 is neutral. There is no charges on hydrogen when it's in this state. So you go from H plus into H neutral. That's how you should see it. And so that means it gained an electron because that plus charge is gone. So for this, you need to gain an electron to cancel that positive charge and become neutral. So is reduced into H2 by gaining okay, one electron. It's one electron per atom of hydrogen. So let's say it's two hydrogen plus, because really that's what it is in the equation here. Two of H plus ions are reduced to make one H2 molecule by gaining each an electron. Two H plus, okay, are reduced into H2 by gaining one electron each. So I guess I should show that as a half reaction. We call those half reactions, where you show what happens to the species that is reduced. H plus, it's actually 2H plus. So 2H plus, and they will gain two electrons each. I mean, one electron, but one electron each. Oops, it's minus. Will become H2. H2. Right? Hopefully it makes sense this way. So we had two H plus ions. They each gain an electron, and together they bind to make the H2 molecule. But hydrogen as an atom has been reduced because it gained an electron. The half reaction for the oxidation would look like this. So aluminum is a solid, so just aluminum. And it lost electrons, so you need the arrow right now. And it became Al. 3 plus. And we lost 3 electrons, so those electrons are showing up here, detached from aluminum now. Let me put parentheses in there. Okay, so that's the half reaction for the oxidation. Aluminum becomes aluminum 3 plus by losing 3 electrons. And those electrons will go to hydrogen and reduce it to H2, hydrogen plus, to become H2. Does it make sense? I know acid-base reactions are really hard for students. So I'm not asking you to know how to write the half reactions because of that, because I know it's hard. I'm only asking you to recognize which one loses electrons and which reactant gains electrons, and so be able to say this reactant is oxidized, this one is reduced. We don't ask you to write the half reactions, but you should know that it's how we do it. So let's do the next one. So we have sodium as a solid. Remember, sodium is a metal, so as a solid, a piece of metal, plus oxygen gas. It's yeah, very reactive, and it makes Na2O a solid. So it gets oxidized. And so which one of Na or oxygen is oxidized? Answer in the chat. Yes. So Na here in its elemental state as a solid, as a metal solid, it's neutral, right? It's neutral. And so to find out what it becomes here in the Na2O, you need to undo this formula and realize that's an ionic compound, right? Because it's made of a metal and a non-metal. So it's made of ions because it's an ionic compound. And so you need to retrieve the ions. And we actually know Na, it's always making the same type of ion. It's a predictable ion. It's in group 1A. It's an alkali metal, so we know it's Na+. So in there, it's going to be Na+, and then oxygen is also a predictable ion. Let me say that. So Na makes the Na plus ion, group 1A. And oxygen makes the, so what is the charge on oxygen when it's an ion? You can tell me? So oxygen is in group, yes, in group 6A. So you do 6 minus 8 and it's -2. It's -2 because it's a non-metal, so it's negative. All of these are superscript. Makes the O2 ion. And so you can see that Na plus and O -2, when you do the crisscross trick, you get Na2O, right? So this tells you what ions you have in this formula. And together they make Na2O. So maybe I should specify the ionic compound. So so that tells you Na from on the left side is neutral, and then on the right side it's a +1, right? So Na is oxidized into Na plus, right? Going from left to right, sodium as a metal is neutral, and it will become Na plus in the compound Na2O. So it's oxidized because it becomes a positive ion by, we become a positive ion by losing electron, losing 1 electron. So if we write the, I'll just write it because for you to get used to see that. So Na becomes Na plus an electron. Right, so it's oxidized by losing an electrons. And then automatically, if the first reactant is oxidized, then the second one is reduced, right? There's no other way around that. So O2 is reduced into O negative 2. We saw that in Na2O, it's in the form of the oxide ion. So be careful. Here it's O2 as a subscript. The 2 is a subscript that says you have 2 atoms of oxygen in that molecule. And it's reduced into O negative 2 here, but the oxide ion with 2 negative charges. So it's 1 oxygen with 2 negative charges, right? So be careful, it's not really not the same thing. By gaining how many electrons? It's actually, again, it's going to be 4 electrons there. So we need to see the, I wanted parentheses there. So let's look at the half reaction to understand why so many electrons. So we start with O2. And the 2 here is a subscript. It tells you you have 2 oxygen atoms bonded together to make a molecule. So it will gain 4 electrons. We will see why as we go. Negative here. So gains 4 electrons to become, and here we have to have a 2 in front, because you see we had 2 oxygen atoms and we are making 2 oxide ion, but each oxide ion is 1 oxygen, right? So that's why the 2 now is in front. You're splitting that molecule made of 2 atoms into 2 ions, and each ion carries 2 negative charges. Like that. So yeah, I didn't say that earlier, but those half reactions, they should be balanced as far as elements, Na plus. There's one Na on each side, but they also need to be balanced as far as charges. So for example, if we look at the Na becomes Na plus plus electrons, Na on the left side was neutral, and on the right side it's neutral again, because you have 1 positive charge on the sodium and 1 negative charge in the electron, and together they cancel and make a neutral. The side of the product is also neutral. If you look above, like with aluminum, that was the same. Aluminum on the left was neutral, and then on the right side you have 3 positive charges on aluminum plus 3 electrons. They all cancel out and it's also neutral. Same thing with 2H plus 2 electrons. That's 2 positive charges plus 2 negative charges, and it's neutral. And on the right side, it's all neutral. So here, to make it neutral, that's why we need to have 4 electrons, because if we look at oxygen, so imagine those 2 atoms of oxygen together, it's neutral. You split the molecule and separate the 2 atoms. So now you have 2 oxygen atoms separated. So that's why the 2 now is a coefficient in front of the oxide ion. And each atom gained 2 electrons. Because you have 2 atoms, then that's why you have 4 electrons. One will take 2 electrons, the other will take 2 electrons. So that's why it's 4 electrons on the left here. And if you look on the right, you take the 2 in front here, the coefficient, multiplied by the 2 of the charge, and it's also 4 negative charges on the right side. So that's why this half reaction is also balanced as far as electrical charges. Oops. Okay. Okay. I know it's kind of difficult, but again, as I said, what I need you to be able to do is to say that oxygen is reduced into O negative 2, the oxide ion, in this reaction, right? And recognize that the sodium is the one that is oxidized. by losing electrons. So yeah, I don't want to insist more on oxidation-reduction reaction because that's all we ask you to be able to do. So you have some practice in the homework. In the lab 4, it's you have to write balanced chemical equations. Yeah, I'll have to look at that again before I talk about it again. Anyway, I don't think the class is ready to do the lab 4 yet, because lab 4, as I said in my email this morning, is dealing with you know, those chemical equations, writing chemical equations, balancing them, and then calculations of moles and grams from moles and grams of a substance from grams of another substance. So this is all about chapter 5, which is to be studied this week. So it's too early to talk about that yet. Well, my review now is going to introduce moles. I know some of you here have, sorry, I know some of you have started chapter 5 already. So you should be able to continue here with the, sorry, hold on, I need to drink. So the chapter 5 is taking a turn from that point on, and you will have to do some calculations. And chapter 1 prepared you for that, right? That's why I insisted on you trying to do the conversions the way it's taught in chapter 1, because here you will have to do it this way. And you will see that by the end we will have 3 conversion factors. So that's why it's important to know how to do, to change an equality into a conversion factor, cancel units, and find out what you want this way. So let's go through the problem 4 here. How many molecules of CH4 are in 3.4 moles of CH4? So let's start with that question. How many molecules of CH4 are in 3.4 moles of CH4? So here it's talking about moles, which in chapter 5 you're told that 1 mole is equal to 6.022 10 to the 23rd particles or things. And what we call particles in chemistry are molecules, atoms, formula units for ionic compound. So molecules here are what we call particles. So definitely you will need to use this relationship between the moles and the number of particles, which comes from the definition of the mole. So let me write this. So 1 mole of, and you need to adapt. So say what you have here, it's CH4, 1 mole of CH4. CH4, no, just the 4. 4 is a subscript here. It's a molecule made of 4 hydrogen atoms bonded to 1 carbon. So 1 mole of CH4 is equal to 6.022 times 10 to the 23rd molecules of CH4. So 23rd is a subscript. Okay. Oh, I forgot to put that in blue so that it's, you know, more visible what I add. So this is the definition of the mole. This is also called the Avogadro number. This 6.022 10 to the 23rd is the Avogadro number. So that definition of the mole is an equality. It tells you that 1 mole is equal to this number of molecules. And that's what will allow you to change. So here the given is our moles, right? Given, given, this should not be subscript. Given are 3.4 moles of CH4. That's what is given. We want, and we want many molecules. So a number of molecules of CH4. Okay, so if we draw a roadmap, and here it's really simple, so you could do without, but you start with moles, you know, of CH4. Moles of CH4. And we want molecules of CH4. All right, so that's the roadmap showing you what kind of conversion we will need to do here. And I think it's a good habit to do that when you need help seeing what, you know, the plan of what you need to do. So that tells you here you will start your calculation with moles, and you always start your calculations with the given amount. And here it's moles of 3.4 moles of CH4. And you see that I write everything moles of CH4. It's because you will see that if you need to take into the habit of writing the units fully, because right now it may not be important. We are only dealing with CH4, but as we do stoichiometry, we will add moles of CH4, and then they will change into moles of something else like oxygen or CO2. And it is important to show moles of what, grams of what, sorry. Because that's the key to know what to do next, you know, how to write your conversion factors. So units are really important, and students tend to neglect that. So I insist that this is important, because it really shows you what to do next. Because here we have moles of CH4 as the numerator, as the given amount, and we need to convert that into molecules. So we need to cancel the units of moles of CH4. So that tells you moles of CH4 will appear there on the denominator of your conversion factor, right? And so our equality was saying 1 mole of CH4 here. So we know it's 1 mole of CH4. And the equality says it's 6.022 times 10, times 10 to the, to the 23rd. And that's a number of molecules of CH4, right? So you see right away we are able to write our conversion factors because we pay attention to units, right? Starting units need to be cancelled with the denominator of the conversion factor. Yeah, I cannot do those lines that show how they cancel those units of moles, but here you would cancel moles of CH4, and you will be left with molecules of CH4. And I'm writing the unit already because we know it's what we will get according to how the units cancel. So in the calculator you do 3.4 times 6.022. Second, EE key so that you have the capital E up here and just write 23rd, the exponent, equals 2.047, etc. I think I have enough sig figs for now. So it's not rounded yet, right? I'll just show everything. So that's the calculator. Oops, I forgot the times 10. Do not forget that, because then it's not, absolutely not the same value. 10 to the 24th, my calculator says. Oops. 10. Right? Don't forget to report everything from the calculator. So 2.047 times 10 to the 24th molecules. And we need to round. So 1 mole is exact, 1 mole of CH4. With the Avogadro number has 4 sig figs. And the given amount has 2, so we need to keep 2. So we keep the 2. Where am I? Oh, not here. Here. 2.0. What comes after the 0 is a 4, so you need to round down, which means you keep the 0 and you drop everything after that. And then we'll copy this. Okay, times 10 to the 24th molecules of CH4. And that answers the question. Right? Do you have questions? So what is the mass? And maybe I should put that question there, because what is the mass in grams? You know, typically it's implied that it's in grams, but I put it there just to be sure. What is the mass in grams of 3.4 moles of CH4? So when you have a question that is asking for grams and gives you moles, or the reverse, you know, gives you grams and asks for moles, you should automatically think. So tell me, can you tell me what you should think? What relates grams to moles? The molar mass, right? You should automatically think the molar mass. Because what relates grams to moles of a compound is the molar mass of that compound, right? So to answer that question, we will need the molar mass of CH4. So let's start by asking what is given. So what is given is the same thing as earlier. It's the 3.4 moles of CH4. But this time, instead of changing that to a number of molecules, we want to know grams, or mass in grams. Mass in grams, right? So if we do the roadmap here, let me take this, copy it. So we start from moles, but this time we don't want molecules, we want grams of CH4, right? So it's one conversion factor because we have the molar mass that relates the grams to the moles of CH4. So let's write this molar mass. I'm gonna be on the other page, I guess. Yeah, 1 mole of CH4 equals. So how do we get the molar mass? It's not given to you. Typically, you have to grab the periodic table. So again, another thing that should become automatic. Whenever you think molar mass, take out your periodic table and calculate the molar mass by adding the mass of each element and multiplying by the subscript. So here, the molar mass of CH4, you take 1 1 time the molar mass of carbon, so 12.01 grams of, grams of C, plus, I will show how we do this for this one, plus the molar mass of hydrogen, because we have hydrogen, and we have 4 hydrogens per formula. So we need to multiply by 4 times 4, so that these are grams, times 4H. So in your calculator, you do 12.01 plus 1.01 times 4, 16.05 grams per mole. So the unit of molar mass is grams per mole. Well, yeah, I wrote 1, and so I guess I should, let me rewrite this. Okay, first, when you calculate the molar mass, you could write molar mass, molar mass of CH4 is 12 grams of C plus 4 times the grams of H, and that's 16.05 grams per mole. The units of molar mass are grams per mole. But then you can rewrite this molar mass into an equality that says on one side you have 1 mole of the substance, and it's equal to 16.05 grams, right? Grams of, and here you could add the formula, grams of CH4. So 1 mole of CH4 is 16.05 grams of CH4. So that's an equality you obtain from the molar mass. And from any equality, you can get 2 conversion factors. But here we will start with moles of CH4. So 3.4 moles of CH4 and we will multiply that by, oops, times. So multiply the moles of CH4 that are given. So always start with the given amount. The given amount is in the numerator. And so to know how to write the conversion factor, you have to keep in mind that you want to cancel the moles of CH4, the units. So you want to use your conversion factor such that the part that has the moles of CH4 will be on the bottom. And so 1 mole of CH4 will be on the bottom. 1 mole of CH4. And then the 16.05 grams on top. So sometimes students get confused. The number with the decimals is the side with the grams. And on the other side, it's always 1 mole of CH4. You always take 1 mole to get the molar mass. And that's it. So you cancel grams of CH4. So let me specify here, it's grams of CH4. You cancel moles of CH4. I don't know what I said, but I think I said grams, it's moles. You cancel moles of CH4 and you're left with grams of CH4, right? You can already write that that's what our unit will be. So in the calculator, you do 3.4 times 16.05, and that's 54.57 grams of CH4. So that's the calculator answer without rounding. So I'll just make this blue and big. So again, the 1 mole here is exact. The molar mass has 4 sig figs here, and the given amount of 3.4 moles has 2. So we need to keep 2 sig figs. So we keep the 5, the 4. What comes after 4 is a 5. So you need to round up. So your 4 will become a 5. And then there was the dot. So you drop everything after that, and then it's grams of CH4. Right? So that calculates the grams of CH4. So, by the way, are these answers making sense? Okay, if we look at 1 mole of CH4, it's 16 grams, about 16 grams of methane. By the way, CH4 is methane, natural gas. And now we have 3.4 moles, so almost like 3.5 moles. So you should have a mass that is about 3 or 4 times the molar mass. And so 16 times 4 is about 55. So that's, making sense. And above here, so when you are finding grams, it should be a reasonable number like this. Moles are always also reasonable numbers, sometimes small, 0.0 something, rarely big. And when you calculate a number of particles, or like a number of molecules or a number of atoms, it's gonna always be a number with times 10 to the 23rd or close to 10 to the 23rd. It's always going to be a number as large as the Avogadro number, right? So if your answer for a number of particles is not having the times 10 to the 23rd or so, then something is wrong in your calculation, right? The number of particles should always be huge, because atoms are so small that you need so many of them to have a sample that we humans can deal with. So that's why number of particles is always very, very large, like the Avogadro number. So these are simple conversions that introduce the definition of the mole, the molar mass. So let's do problem 5, unless you have some questions. So please don't hesitate to stop here and so let's do problem 5. What is the molar mass of Ca3PO4 2 times? So that's an ionic compound made of calcium, the metal calcium, and then the polyatomic ion phosphate here. And you have 2 phosphate for 3 calciums. So let's calculate the molar mass. And this is really testing you to calculate molar masses. So molar mass of Ca3. So go ahead and calculate it, and we'll see if we get the same thing. So here I'll show the detail because it's a tricky one, unless you have learned already. But so it's important to be able to get the correct number of each element in the formula, right? So here we have 3 calcium, right? The subscript 3 means we have 3 calcium per formula. So you will do 3 times the molar mass of calcium. Again, to get the molar mass, you need the periodic table. I don't need to show it, I hope. But calcium has a molar mass of 40.08 grams. Plus. So 3 times 40.08 grams of calcium. Then here you have to be careful. So you have PO4 in parentheses, and there is a 2 outside as a subscript. The 2 outside the parentheses belongs to everything that is in the parentheses. So you need to multiply the subscript of P with the subscript of the parentheses. So it's an implied 1 times 2. So there is 2 P in there, 2 phosphorus, because you have 2 phosphate ions and they each have 1 phosphorus. So it's 2 phosphorus per formula. So 2 times the molar mass of phosphorus, and phosphorus is 30.97 grams of P. That's phosphorus. Now see oxygen. So oxygen, you have 2 phosphate, and each phosphate has 4 oxygens. So you do 4 oxygens times 2 phosphate, and that's 8. So you have 8 oxygen in total there. So 8 times the molar mass of oxygen, and equal. Right? So then you add everything. So 3 times 40.08 plus 2 times 30.97 plus 8 times 16. And so the molar mass of calcium phosphate is that 310.18 grams per mole. Right? So that's how you calculate the molar mass. Next, it's asking how many grams of calcium phosphate do we have when we have 7.3 10 to the 24th calcium phosphate formula units. So yeah, we don't say molecules because it's not actually proper to say molecules when you have ionic compounds, because molecules is really a term that only applies to covalent compounds. You know, like above we had the CH4 molecules, that's a covalent compound, and we call also them molecular compound, and so then it's molecules. But when you have ionic compound, we don't call them molecules, and that's why we say formula units. So if you see that, don't be surprised. It really means, you know, units of one formula, which you can take as a molecule, right? In your head, you can think it's a molecule and it's fine. So how many grams of Ca3PO4 do we have when we have 7.3 times 10 to the 24th? So that's our given. It's the amount of formula units, or you can see them as particles. And I will copy that because formula units, you can also see them as particles. Particles of Ca3PO4 2 times. So we have this number of particles or formula units, and we want, what do we want? How many grams? So grams of Ca. So we want to know what is the mass of this amount of particles. So if we write the roadmap here, we should have a roadmap that starts with formula units, and we want grams. So I should put in there the formula. Let's see, formula units of that. Okay, I have to. There's a, oops. Okay. 3. Formatting takes a lot of time, but on your paper, it's easier. I have to put the 2 here. Yes, this will go there. Oh, no. Okay, so from formula units are particles of Ca3PO4 2 times 2 grams of that. Ooh, do we have a conversion factor that can do that directly? No, we cannot change particles to grams directly. We don't have you know. So what is the thing that should be converted? The particles should be converted to what first? What's in between? Yes, it's the moles. We need to change to moles from formula units to moles and then from moles to grams because we don't have um, uh, equivalence directly from particles to grams. Okay, so that's why it's a good idea to write your roadmap or show you what uh, steps you will need to do. And so whenever you have an arrow, this tells you you have a conversion factor there. So here there will be two conversion factors. The words here symbolize what you start with, the given amount, what you will calculate in between if you were to calculate it, the intermediate answer, if you will, and then the unit of the final amount. So then let's start our, well, we don't have our equivalences yet. Well, we have the molar mass. Remember how the molar mass, let me remove that first. Remember how the molar mass here can be written as an equality that says 1 mole of CaSPO4 2 times equals grams of that, right? So we have this. Oops. We have this equality. That's going to allow us to change moles to grams or grams to moles. Oh, yes. And we need, so that's going to be the second conversion factor. And we need the first conversion factor between formula units and moles. So before that, we need another one that will relate the moles to particles, to formula units. And that's the Avogadro number, right? So 6.022 times 10 to the 23rd. Okay, so 1 mole of this compound is made of 6.022 10 to the 23rd formula units of the compound or particles. So we have our two equivalences, which means we have our two conversion factors. And we can start the calculation. So always start the calculation with the given amount, 7.3 times 10 to the times 10 to the 24th. Oops. And that's, okay, we'll put, it's a long formula, calcium phosphate, so C calcium. Well, I'll have to do that formula. Oh, I have it here, I can copy it. Of that, units, I will just write units to tell particles. So that's the given amount of particles. And we will multiply by the first conversion factor. and then there will be another one. So we have formula units, and we want moles at first, right? The first conversion factor needs to change the particles into moles. And here we have this definition of the mole that relates particles to moles. And we want to cancel the formula units because that's what is in the numerator of the given amount. So then we will have the formula units on the bottom there. So let's see if I do that. Yes, units will be on the bottom, but it's a 6.0. It's the Avogadro number of units. Oops. 2 times 10 to the 23rd, the Avogadro number on the bottom, and then the 1 mole on top, 1 mole of calcium phosphate. This way you cancel the formula units, and you have the mole of the compound on top. The intermediate unit now is moles of calcium phosphate. So when you think about the next conversion factor, you want to cancel this intermediate unit of moles by having the moles in the denominator of the next conversion factor. So we will want 1 mole of this compound in the bottom. And here we want to convert to grams. So we use the molar mass here. And so the 1 mole is on the bottom and the molar mass is on top. So if we look at this carefully, we cancel, and I cannot show that, but you cancel units of calcium phosphate, particles there, number of particles. You cancel moles of calcium carbonate, and you end with grams of calcium carbonate. So that's correct as far as units are concerned. So in the calculator, you do 7.3 times 10 to the 24th divided by 6.022 10 to the 23rd. So be careful when you are dividing by the Avogadro number. It's very important you use the EE key, because if you're dividing and not putting parentheses, the calculator will move the times 10 to the 23rd to the numerator if you have not specified it's part of the denominator. So by using the EE key, the calculator will know to keep that together. The 6.022 and the times 10 to the 23rd, they will keep it together. And then we multiply by 310.18. And that's a big number, which makes sense because we have more than 1 mole. Okay, the calculator is 3760.069, etc. So I give more digits because we need to run that. Okay, so look at the value, 3,760 grams. It's a lot. The mass is large here. But if you think about it, we started with 7.3 10 to the 24th units of calcium phosphate. And if you look at the exponent, 10 to the 24th is 10 times more than the Avogadro number, right? So that means you have 10 moles, right? If it's 10 times more, that means you potentially have 10 moles here. 10 moles of calcium phosphate would multiply its molar mass by 10. And we have 310, so times 10. Then that's why we have a mass in the 3,760, because it's even more than 10 times, because it's 7.3 versus 6.2 for the Avogadro number. So that's why it's even more than 10 times the molar mass. So the value makes sense here. Let's round it. So the Avogadro number has 4 sig figs. The 1 moles are exact. The molar mass has 5 sig figs. And so the given amount is what limits the number of sig figs to 2. 7.3 has 2 sig figs. So here, 3,700, so we keep those 2 digits. And then it's 60.0 something. So we keep the 3, the 7. And then what comes after the 7 is a 6. So you need to run the 7 into an 8 and then drop everything after that. However, the 3 is in the thousands place and the 8 is in the hundreds place. And you need to show that by adding zeros to show the thousands place for the 3 and the hundreds place for the 8, right? So that's why you need to add those zeros. Do not show the decimal point, because otherwise it would make 4 sig figs. So to keep it 2 sig figs, you just have it like this. Oops, what happened? Here, grams of, and that formula. So that finishes that problem 5.